a man from Google. Mr. Jack Architect, as his friends call it, or Jake Archibald. It's his birthday today, so let's all enjoy him.
Happy birthday to you. Happy birthday to you. Happy birthday, dear Jay. Happy birthday to you.
On his 40th birthday. I give you Jake Archibald, Streams of Shit.
Yep, excellent, cool. Someone tweeted a few days ago saying, like, wow, Jake's going to be talking about something other than service workers. They are going to be very disappointed. So I'm going to talk about this, which we saw before. This is the wiki offline thing that Junki was talking about. This is the URL site. You've probably seen that already. So the reason I actually created this is I wanted to show that service worker could be used for something less app-like, because most of the demos were very, very app-like until then. Without service worker, it's all server rendered, very much like Wikipedia is. My eventual aim was to make it work offline, which you saw in the demo earlier. But as a first pass, I just wanted to add service worker in as a kind of performance enhancement. So I built a page shell. We saw the kind of application shell article before, and this is a pattern I was following. So I served this up. This is just the header, it's got the footer and the references to the scripts, like the CSS and the JavaScript. And I cached that as part of my install events. In my fetch events, I'm just going to look and see for all the requests that start with /wiki/, and if they do, I serve up the page shell. Because /wiki/, that's all of the articles. Otherwise, it would serve from the cache, and if there's no match in the cache, then it would serve from the network. So for these article pages, it would load this generic shell that you saw before, and then the page's JavaScript would figure out which article it actually needed to be displaying at this point. So without service worker, it was just like any other website, but with service worker, I kind of re-architected it into this kind of single-page app structure. And then so I wanted to kind of compare it and see the difference I made. So I pitted it against the normal server render without service worker, and then versus the service worker enhanced version. And so this is not an article that's cached offline. It's still going to be loaded via the network. I'm going to be loading it through a throttled internet connection, or as most of the world call it, their internet connection. So on the left, first version. On the right here, with service worker. Go! And when I did this, I couldn't help noticing it got slower. So here it goes again. You see, the first render is actually quicker, but the content, which some people would say is the important bit, is significantly slower. It's 2 seconds slower on 3G. At this point, I was kind of filled with dread, where I had to go and talk to the junkie and say, like, this service worker thing that we've spent years designing wasn't actually fit for purpose, it was making things slower. But it wasn't actually service worker that was the problem. So I was using this page shell and letting JavaScript do the rest. I'd re-architected a site into a single-page app. And single-page apps are incredibly slow, and this is why I moan about frameworks all the time on Twitter. So here's what it takes a website to render. The HTML starts downloading, the CSS downloads, and all of that needs to download. And now we start rendering content. And we continue to render content as the HTML downloads. We might download JavaScript too, sure thing, but it should be async, it's not going to interrupt the rendering of the page. Contrast this to single-page apps, where the HTML downloads, usually instantly, because it tends to be very small, empty body tag in some cases. CSS downloads, all of that needs to download. And then we get the first render. And that's assuming that JavaScript isn't render blocking, which is, I don't know, it's a pretty kind assumption to make. Let's make it here. Let's assume it's loading async. But anyway, this first render is just a basic UI render, no content. And then the JavaScript has to download in its entirety, and it needs to parse and execute. And then it goes out fetching content. And once it has all of the content, it adds it to the page, and you get the render. This is where the slope happens. And actually, in my case, I didn't lose too much on the CSS, the HTML downloading, the JavaScript downloading, because I was just pulling those from a service worker cache. But it's just a problem, this is very important here. The JavaScript has to download all of the content before showing any of it. The more I think about load time performance, the more I realize it's not about the size of the CSS, it's not about the size of the JavaScript. It all comes down to being progressive. And this is related to progressive enhancement, but not quite the same. I kind of mean, just show them what you've got. Like all the time you're loading, the user is watching and waiting. Don't make them wait until you've loaded everything before showing them anything. Like prioritize the first render, prioritize the first interaction. Show the user what you've got as you get it. And that's where I was failing, because I was pulling down the entire article before I show any of it to the user. I was hoarding content. In retrospect, it kind of seems pretty stupid, really, to try and cram a site into this page shell model. But for me, this was actually my app cache hangover, because app cache nearly lets you use this page shell architecture, but not quite. But it does let you so close you can almost smell it, but it won't let you have it. So once app cache was out of the way, I was like, really? App cache is gone? Does that mean I can have all of the page shells I want, and no one's going to stop me? But I didn't stop to think that the best answer wasn't the one app cache nearly let me have. It was the thing it never let me anywhere near. What I wanted was streaming. So with streaming, you can finish a kind of simulation of streaming. So it's the same bit of data traveling at the same pace, but you can see with streaming, it finishes a little bit faster. And the reason it finishes a little bit faster is the processing could happen while the fetching was happening. But the important bit is something can render way sooner. So you get your first render here, meanwhile the fetching is still happening and the non-streaming version happens much later. This is the full HTML spec loading here over a photo connection. It's a 3 megabyte document. It's still downloaded, but it gets on screen after only 20k or so is received. And that's the power of streaming. It's something the web's been doing for like 20 years. But for a long time we had no access to these streams in JavaScript, but that's all changing thanks to the extensible web manifesto. So the design fetch alongside service worker, it was specified by Archibald and he opted the design as well. So we wanted it to be a kind of lower level representation of requests and responses. It was also a good opportunity to do a better API than XML HTTP request. So you fetch a URL, and that returns you a promise for a response. Now this promise resolves when we have the headers for the response, and we know that due to the security of the web, we know we can give you it back. But we might not actually have any of the body of the response yet. Then you can read the response however you want. In this case, JSON. And that also returns a promise because it's not there yet, and then you can say whatever. And this compresses down really nicely using ES6 arrow functions, and even nicer with async functions. So I don't know if in case you haven't encountered these before, the keyword awaits there, followed by a promise. It will kind of pause the execution of the function until that promise resolves, and then it gives you back the eventual value, or it throws if the promise rejects. It's only Edge in one of their experimental builds that has limited support for async functions today, but Babel lets you use it in other browsers. And I think this stuff produces really easy to read code, because you can kind of pretend async code is synchronous, but it doesn't block the main thread. It's not like a synchronous XHR where everything gets locked up. And you don't have to read the responses as JSON. You can use all kinds of other formats, form data, which is useful more for requests and responses, text, log, arrays, other more lower level formats. So we added these for 2 reasons. They're nice convenience methods. They're kind of the really common cases. But we also wanted to ship fetch before streams were standardized. Because we knew the stream thing was coming and we knew we wanted it to be part of the fetch spec. So we reserved response.body and also request.body, and we said that's where the streams are going to go. The response.body actually landed in Chrome and Opera around a year ago, so it's been there for a while. It's been actively developed in Firefox, Edge, and even Safari. Here's how you use them. So I'm going to fetch the HTML spec, because it has course headers, so it's something we can do. But we want to read it as a stream. So First I call on response.body.getReader, and that gives me a lock on the stream, because only one person can read the stream at any point. Once I've got a reader, nothing else can read it unless I release that reader. Then we can read some data using reader.read, and that returns a promise. I'm going to wait a minute there. I'm going to use the async function stuff a lot in my code because it produces nicer to read code. The result there is an object. Result.done is true if the stream is over, if it's given all of the information that it's to give. Otherwise, result.value is a bunch of data. And in this case, the chunk of data is going to be something like this. It's a UINT8 array of bytes being received. This is a really low-level API, so you can use this for things like audio, video, images, and it will give you access to the raw bytes that come down the wire. This is not the whole response, this is just the first part of it. If we want the second part of it, we call read again. Now it gives the next bit, and on until result.done becomes true. So we wanted to get the length of the whole response. We can do something like this. So I've got my reader, and I'm going to have a variable there for the results, and I'm going to keep a count of the total. Then I'm going to create a loop. So this is calling read on each iteration, so awaits read.read, store that in results, and it's going to keep doing that until result.done is true. And inside that loop, I'm going to look at the value I get and get its length and add that to the total. And then you can log that out. You can see that working, hopefully. This is up here. So this is the log down here, and you can see that the bytes are all roughly the same size, but they're not always, so you can't expect them to be a particular size. And there it is counting up. Some of the chunks will be small for whatever reason. It's just kind of, you just have to deal with whatever the server or browser gives you. Eventually, this is the HTML spec, it's quite large. It's around about 8 megabytes. So here we're actually inspecting parts of the response, but we don't need to keep the whole response in memory at any point. So there's over 8 megabytes of data, but we never had to allocate 8 megabytes of space to deal with it. So a more practical use of this would be to search a stream for a particular string. So say we wanted to search the HTML spec for the string horse. So we can do this, fetch it, ask for the text, and then see if there's include the word horse. But this means reading all the text into memory, 8 megabytes, and then searching across it. We can do this a lot better with streams. So here we are, moving over the stream again as we did before. But the problem here is result.value is an array of bytes, and we need a string to want to do string matching. Now in future, this will actually be quite a simple problem to solve. We can just create a new text decoder which will become a transform stream and pipe our stream through it. So a transform stream is going to take bits from one stream, modify them in some way, and pipe it out the other side, and it returns its own stream to do that. So here we return something that's returning chunks of UINT8 arrays. It would now be chunks of strings. But transform streams are not being fully specified yet, so we kind of have to do it a little bit manual in the meantime. So we fetch, we get a reader, but we also create a new text decoder. Text decoders are part of the text encoding spec. It's been around for a while. I think all browsers support it. But once we have that, we can loop over the stream, and in the loop we pass result.value to decoder.decode, and that takes those bytes and converts them into a string, assuming UTF-8, which it usually is. The stream true, this option here, this is really important. Without that, things can break. So here I've got 3 chunks of data, 3 UINT8 arrays. Each one's got 3 bytes in it. I'm going to create a text decoder, and then for each part in those parts, I'm going to decode it and log it out. And as you can see, everything has gone a bit broken. It's broken text. But if I add string true to it, and now it's changed and it works. We get an empty string, the true emoji, and the toilet emoji, and making them up. So the reason this happens, it's my birthday, I can do what I want. So the reason this happens is these emoji are actually represented by 4 bytes each. Most characters are 1 byte. Other languages, you'll start to get multi-bytes and emojis that are 4. So with the stream option, it knows that the next thing you pass it is going to be a continuation of the first thing. So the first time we call it, it receives these 3 bytes, and it goes, well, this is not, I know this is part of a character, I know it's not a complete character, so I'm going to just hold on to those 3 bytes and return an empty string. The next time around the loop, it gets this 169 and it goes, oh, I'm going to add that to what I've already got. Right, I have a poo emoji, and these 2, that's partial, so I'm going to hold on to those last 2 bytes and return the poo emoji. The next time round, it will get these 2 bytes, add them onto what it's got, it goes, this is a toilet emoji, and then the 33, that's an exclamation mark, and it can send out the full string. When you don't tell it it's a stream, it assumes that each thing you pass it is a complete set, is a complete string. So it goes, well, I don't know what this is, and confused by the So now we've got our string, our text. We can now look to see, does that include the search term, and if so, we can log it out. We can also cancel the stream. This is really useful because it means that we found our match, and now we can halt the download. This is an 8 megabyte document, so if we can find a match in the first 100K, we can stop the download and save the user's bandwidth. But this is actually a pretty buggy implementation. It's got one main bug when it comes to chunk boundaries, which sounds like an action hero to me, chunk boundaries. But so this will work fine if our chunks are something like my lovely, no match, pause running through the field. Right, there's a match, so we can stop and pause. But what if the chunks are my lovely, no match, pause running through the field, no match? So we miss the match because neither chunk contains pause. So when you're doing things like searching streams or filtering streams, you need to defend against this particular bug. What you need to do is you need to keep a buffer that's the size of the thing you're looking for, -1. So in our case, horse, 5 characters, we need a buffer of 4. So that means we would see my lovely her, no match, but then we would retain the last 4 characters, LYH, we'd add that onto the next chunk, and therefore we would see horse, we've got a match. So the code for that, same as before, I'm also going to retain a buffer, it's going to be empty at the start. We loop through the stream, and I'm going to add what I decode onto the buffer, look for a match in the buffer, but if there isn't one, reduce the buffer down to the last n-1 characters. So the last 4 characters in this case, we go back around the loop. So now we're searching a large document, and we're keeping the memory usage down, and we can stop the download early, which is pretty good. So this code's a little bit more complicated because it's case insensitive, because you have to cater for that, and I've also keeping more context either side of the match it finds. So if we actually run that for the HTML spec, there is a match for horse because someone contributed to the spec called Tommy Forson, and he's the one with the horse in his name. Any other suggestions for things that might but unlikely be in the HTML spec? Anyone? Horseshit. I can guarantee you that's not in there because this is right at the end of the document. So unless someone has a really unfortunate name, Jimmy Horseshit. I just out of curiosity, I wonder if I can actually search the tech and see. Oh my god! How much shit leaked to Right, I thought the whole example was funny. I'm stealing this one. So I'm just developers in India, and connectivity is pretty poor. And they were sending a blob of JSON down for some search results, and then having JavaScript display them on the page. And they were saying, we want to be able to detect 3G versus 2G. So, and this is an API we actually have in the browser, navigator.connection, and it's just sort of guessing due to what the phone thinks it's connected to. Like the same thing that produces a little icon across the top. As you know, like whatever that icon says doesn't necessarily mean how fast you get data. So I was saying, like, why do you want to detect 3G versus 2G? And, we want it to create a faster render. So if they're on 2G, we'll send less results than if they're on 3G. We'll send even more results if they're on 4G, if they're on Wi-Fi. Because it's less to download, because if you have JSON, you have to download the whole chunk before doing anything with it. But yeah, detecting this kind of connectivity is really unreliable. So the idea I gave them using streams is to instead serve this, which isn't JSON, but every line in the file will be JSON. So you can stream that and you can deal with every line as it arrives and then parse that line as JSON and do something with it. So now dealing with the first result isn't dependent on receiving the last. So I think. Oh. So, I mean, whether this is a benefit depends highly on the connections. So, if I fetch regular JSON, this might not work. So, what we're saying, 200, 500, 300, 300, we would stream it. So, it's kind of not too different, but let's see if I throttle the connections so we can see something different happen here. Should refresh before throttling the connection. Right, so fetching regular JSON over a throttle connection. Yeah, okay, that's messed up. Maybe I've gone too slow. Come on, do something. Sorry. Let's go regular 2G. Yeah, it's not fantastic. Let's go again. 2G. I had this demo on the tray. Okay, 4 seconds, that's good. But if we do a streaming version of that, hopefully it will be faster. There. So now we're able to deal with that first bit of data. Like, normally it's going to take like almost 5 seconds, and it's still going to take 5 seconds to process that entire data set, but we can do something with that first item in just 600 milliseconds. Also, I love JS thing. I love the URLs it generates. This one, as I say, just go through this together this morning. This sounds like a kind of insult to a CDN provider. It's like more like Kakamai. Jen actually gave me the URL Game Boy there as well. I'm a proud owner of that. Right. So you might be wondering how I can use all of this to speed up my Wikipedia demo. Well, I can't, because although you can use like fetch to read the response in little chunks, JavaScript has no access to the streaming HTML parser. Here it might look like I'm merely adding HTML into an element, but plus equals is the same as getting and setting at the same time. So you're asking the browser to serialize all the content of a string, and you're adding more string and asking it to parse it. So the elements at the start of the string get created loads of times. It's a real performance disaster. I hope we can get an API soon where you can actually stream a string into an element. It's not there yet though. But in Chrome Canary, you can actually create your own readable strings. It's like that. That's all it is. You pass an object in with some of these methods. You don't need all of them. So say we wanted to create a stream of random numbers. So I'm going to have this bar here for an interval, and you'll see why in a moment. I'm going to create a stream, then I'm going to pass in this start method. This is called straightaway. It's a good way to set up the stream. Here I'm going to set up an interval that pushes a random number onto the stream every second. And it's controller.onCue to pass an item into the stream. There are other methods on controller like .close to signal the end of the stream and .error to signal an error. I'm also going to add a cancel method. This is called when the reader cancels the stream. So we're going to take that opportunity to cancel the interval. So now this can be used just like fetch streams. So here's the same code you saw before, but I'm also getting the reader, reading 3 values from it, and then cancelling. And you can see this little log output there. So you can see as it runs, every second we're getting the value through, and then we cancel, and we ask for the next value, which gives us done true, because we cancelled the stream. So this is a push stream, in that we are pushing values into the stream, whether people are reading it or not. And this kind of has the unfortunate effect that if no one's reading the stream, these values are just going to be buffering up in memory, waiting to be read, and eventually will cause memory problems. The opposite of this is a pull stream. So the pull method is called when a reader is waiting on a value and there aren't any left in the buffer. So here I'm going to wait a second using promise and then push a random number onto the stream. This is much better because we're not generating random numbers if there's nothing reading the stream. And the streams can be of anything. Now, we saw it fetch, so where you intake arrays. Here, there are numbers, but there can be objects, there can be elements, there can be images, there can be whatever you want. The designers of web streams, like Dominic Penicola, the main designer, spent a lot of time talking to the Node folks because they had like loads of iterations of streams, and they've got because they were a good source of here's all the fuck-ups we made, here's all the problems we have. And one of those mistakes was having different kinds of streams for different objects, so that doesn't happen here. So you might be wondering how I can use this to speed up my Wikipedia demo. Well, I can't. Not just using streams on their own anyway, but things get a lot more interesting when they're combined with the service worker. So this already streams. Like the browser knows, fetch a network request, it gets a response back, and it streams it directly into the browser. This also streams, caches.match. It's streaming from disk this time rather than the network. But in Chrome Canary, you can create responses from your own streams. So in my fetch events, I'm going to create an encoder. So this is the opposite of before. It's a text encoder. So it's going to take a string and produce an array of bytes from that, which is what response streams need. Then I can create a stream that has a pull method as before. It's going to wait a second, and it's going to push a paragraph to the stream containing a random number. And in there you can see encoder.encode, which will take that stream and convert it into a byte array. Now I'm going to create a response. The first argument of a response is the body, which can be a string, it can be a blob. Here it's a stream, and I'm saying, hey, the headers, this is an HTML resource. So, run that. And then we'll see the numbers appearing slowly. Now, as far as the browser's aware, it's just receiving text very slowly, as it was from the network. And you can see the spinner up here. It's just, as far as it's aware, it's receiving something from the network. You might be wondering how I can use this to speed up my Wikipedia demo. Well, I actually can. Before we were piping content straight into the browser's streaming HTML parser, and that's the key to it all. Like, what AppCache wouldn't let me do is that it wouldn't let me access the streaming HTML parser from a sort of pseudo proxy. So instead of turning a perfectly capable server-rendered site into a JavaScript-rendered single-page app, I can use my service worker more like my server. So what I did to Wiki offline is I fetched the header, the footer, and the body independently. Now the header and footer come from the cache, whereas the body of the article comes from the network. Then I combine those streams together into one single stream. Combine is a function I wrote. It's not very long, but I'm not going to show it. But that's just going to create a stream, start reading from the first stream it receives, and then start just feeding that into the single stream. Once that is exhausted, it moves on to the second, and then on to the third, and then it closes the stream. Then I'm going to create a new response using that single combined stream. So I'm sending out a single response, but it's made up of multiple parts from different places, which is just like I do on the server. Like I get some bits from a database, some bits from disk, some bits from the network. It's treating your service worker like a server maps really well to content sites like blogs and Wikipedia, which are server-driven. The result of this, so comparing from before. So on the left is the normal server render with a full cache. So JavaScript and CSS are all going to come from the cache. And on the right is the streaming service worker thing, the code that you saw before, both over 3G. Go. We get the benefit of that quick cached first render, which happens without the network, but that allows the network stuff to get on screen quicker because there's less fetch. So I'll play it again. Quick first render, fast second render. The first render is almost a second quicker, and the content is half a second quicker to hit the screen, even though it's coming from the same network connection in each example. So I'm really excited about streams, in case you couldn't tell. And I think we're really starting to scratch the surface of what's possible here. Like, there's so much of the web that does streaming, like images, video, and to enable these into this sort of low-level streaming API, I think we're going to see happen over the next year or so. In this post, I do some stupider stuff than we've seen. I actually transcode an MPEG into a GIF on the fly. I don't know why. It's interesting because it means it will autoplay on a phone, which videos don't currently. But it still means that you're using a processor power to decode an MPEG and then encode as a GIF. And I was going to show you that now today, but it's actually broken in Canary. But there's other stuff. So this is taking Wikipedia's article on the cloud computing, but in a streaming transform it replaces cloud with but. And so that means that even as it's downloading from Wikipedia, it can start displaying the transformed version. It doesn't have to receive it all. Here a bit, where is it? Oracle announced the Oracle Bus. All aspects of the Oracle Bus are still in development. This bus offering embodies the. I love that term, bus offering. So on a slightly different subject,